I want to talk about how the upper bound lemma actually connects to all the topics that we talked about before about ergodic theorem and the non-concentration on subgroups and the spectral gap. So if you recall that mu from ZP to 0, 1 has this is a probability distribution, by the way, probability distribution has a spectral gap if the maximum of the Fourier transforms of this k in ZP, k not equal to 0, is less than 1. So if you recall, like the main problematic point is when k is equal to 0, because then the Fourier transform of mu, because the probability distribution, it is equal to 1. So this spectral gap is kind of the main difference here. So now you can very simply see that somehow, if you recall that this mu is, we say it is mixing with rate phi n going to 0 as n goes to infinity if the total variation distance to the uniform is less than phi n. So using this upper bound lemma, we can immediately see that there's actually an exponential mixing, in the sense that we say that mu is exponentially mixing if this phi of n is maybe a constant times e to the power minus alpha n for some alpha positive and c positive. So if you can write it in the form that is an exponential function or exponential rate, then we have an exponential mixing. And the theorem that's saying that if mu has a spectral gap, then mu is exponentially mixing. And the proof is like very straightforward after you use the upper bound lemma by denoting this maximum as let's say a theta. So you take the maximum, so we have the spectral gap in ZP not equal to 0. And now we have that this theta is non-negative and it's strictly bigger than 1, so it's strictly less than 1. And now just by upper bound lemma, we have that the total variation distance, if you fix an n to uniform, this is at most a half of the square root of k in ZP, k not equal to 0, of mu k to n. And now you can see why we define the spectral gap in the way that you exclude the 0, because now you can, in here, you can just simply bound by the maximum. So you can take the sum of k in ZP, k not equal to 0, as theta to the power 2n, because that's the upper bound for all of them. And now in this sum you have exactly p minus 1 terms. So what you get here is a p minus 1 terms, and you take the square root. You just obtain square root of p minus 1 over 2 and t to the power n. That's what you obtain. So you just obtain that this is bounded above by this, and now taking a logarithm, so if I set, let's say, alpha to be equal to the logarithm of this 1 over theta. Okay, here there's a slight worry that maybe what if the Fourier transform is actually equal to 0, like it could be in the case of the Lebesgue measure. So what you could do here is that you could take this, you could define this to be like, if you really wanted to be pedantic, you could define this to be the maximum of theta, maybe a minimum of this these two. So then it's still an upper bound. So you could put here, like I don't know, like this, like a half, for example. Then in that case, you still have an upper bound for this. You can still bound it by the maximum. So this is then positive number. So now you have an expression in this way that this is equal to the expression that we have here is equal to then you could write this as a p minus 1 over 2, and this is bounded above by e to the power minus alpha n. So that's the alpha you could choose, which will be positive because theta is less than 1. So you could make that happen if you want to be very pedantic on the kind of expression you have here. Otherwise, it could be infinity if the alpha is 0. So you could possibly infinity. So if you want. So you have it is an exponentially mixing, and that's the constant depends on the group, so the number of elements in the group, and then you have this kind of an expression. And the second thing that you can see then as a connection, that mu has a spectral gap if and only if mu is ergodic actually. So actually mixing, actually it's the same equivalence. So if you remember, ergodic means that this total variation distance actually converges to 0. So you already have the other direction, because if you have a spectral gap, it's exponentially mixing. So in particular, is it ergodic? So the proof of this to the other direction is then using this lower bound lemma that I mentioned in the previous slides, which was this, that if you take the total variation distance to the uniform, then this is bounded from below by a half of 1 over p, and then you have the k in zp, k not equal to 0, and then you have the mu star k to n. And now you can then use the fact that, okay, yeah, so if the, let's say if mu does not have a spectral gap, then this implies that there exists an L which is not equal to 0, such that mu L is equal to 1. That's the definition of the spectral gap. It has to be exactly, so the absolute value has to be equal to 1. So that's the definition of spectral gap. So now what we can do here is that we can just bound this, because these are absolute values of all the terms. So we can bound it from below by this half. So if this doesn't have a spectral gap, then by the lower bound lemma, we have just obtained this kind of a lower bound. So we have just the term that mu L, so you just use this one to the power 2n, which now, because this is equal to 1, we just get this is equal to a half or square root of p. That's what you get. So you just proved that this expression for any n in n is bounded from below by something which is a uniform constant, which is a positive number. So in particular, this cannot go to 0. This cannot go to 0 and then go to infinity. So not ergodic. So in particular, what we just proved, that if you don't have a spectral gap, you are not ergodic. So that proves that then the opposite is true. So we have that if you have a spectral gap precisely when you're ergodic in this way. So this was like one of the other conclusions that I wanted to kind of say about this. And the final thing that maybe I could mention, if you want to like see the kind of connection to non-concentration, for example, that if you remember that the ergodic theorem was saying that if you are not concentrated on a coset of a proper subgroup, then that happens precisely when you are ergodic. So now we can do the same thing, that this ergodic theorem allows us to characterize spectral gap. So spectral gap happens precisely when you're not concentrated on these cosets of the proper subgroups, okay, which are not like singletons in this sense, like cosets of the trivial subgroup of 0, and this way we can characterize ergodicity and spectral gap and the non-concentration into a single statement, that they are all like in the same same category. So your random walk doesn't concentrate on subgroups if and only if you, or concepts of this kind of proper subgroups, if and only if it has a spectral gap, or if and only if it's ergodic, if and only if it's exponentially mixing. So there's all these stations are equivalent in this setting. And later on we will see that if we go to more general groups, this is not true anymore. So you need to have actually, then you need to talk about normal subgroups, for example. You need to talk about the kind of more precisely what do we mean by this. The fact that if your group is not an abelian group might have some obstructions to this kind of statement, but philosophically there will be very similar ideas that being spread and flattening this, if you're not concentrating on a cosets or proper subgroups, is really the kind of the key thing that you need to analyze. You just need to go more into like if it's like from the left or the right, studying the whether it's an abelian group or non-abelian group. But you can carry this kind of idea with you to these more general settings. And when you use, we talk about representation theory, for example. Okay, so that's all I wanted to mention in this lecture, and in the last lecture of this week I will go a little bit of some examples how to use this to compute some probabilities of random walks, which we kind of a little bit did already in the earlier lecture, but I'll repeat a couple of the examples there. So that's all for today. Thanks.